Hi everyone, this is Error. My voice is a bit hoarse as I'm currently in France, so please bear with me. TSMC has announced that their 2nm process is now ready for mass production. I'll be discussing the current state of the 2nm technology, including its performance and power efficiency. It looks like the first device to feature TSMC's 2nm technology will be the iPhone 18 series. We will briefly cover various aspects, including why it might be worth waiting until that iPhone model is released, how previous iPhone launches have affected sales, and other related topics. As you can observe, TSMC's N2 process introduces the gate-all-around nanosheet architecture for the first time. Even this gate-all-around structure adopts slightly different designs, leading to some variations. Regarding nanosheet and nanowire technologies, I compiled a summary a few months ago detailing the differences between them, so please refer to that. Anyway, regarding the N2 node in TSMC's nanometer process, this marks the debut of the gate-all-around architecture, specifically using the nanosheet design. Keep that in mind as you listen to my insights. Let's dive in. To start, while it's been covered by various outlets, TSMC is expected to ramp up to producing 50,000 wafers per month using the 2nm process by 2025. Depending on the yield rate per wafer, they could produce anywhere from 100 to 500 chips per wafer. With this monthly production capacity, it's estimated that the yield rate has now exceeded 60%, which makes it quite probable that it will be featured in upcoming iPhone models. In this context, if you look at the process roadmap, you can see that the N3 process, which started in 2013, is also referred to as N3B. Following that, N3E became the main focus, with Qualcomm and various other companies adopting this N3E node to apply the 3nm process for the first time. This year, TSMC plans to expand N3P and N3X, and for the first time, apply N3P, N3X, and N2. These nodes, starting with N3, are considered the last processes of the 3nm FinFET technology. As I mentioned in the past, the N3 process derivatives such as N3P and N3X are anticipated to either boost clock speeds or be expanded for server applications. Meanwhile, N3E is essentially the same as the N3B process, which was previously known as N3. In the N3B process, they initially utilized 25 EUV steps. By reducing the number of steps to 19, they significantly lowered the production cost by decreasing the utilization of EUV machines. So there are many fabless companies that want to use the 3nm process. AMD, Apple, Qualcomm, and Intel wanted to use it, but it was too expensive, so they could not use it well. However, they managed to use it efficiently by reducing costs. But the next node, N2, is coming with a gate-all-around structure. Looking at it from this angle, which company is pioneering the use of TSMC's cutting-edge process? It's none other than Apple. Apple has used high-performance chips in iPhones. I've summarized it for you. Here, you can see they used the 7nm process. Then, with the M5, it was for the iPhone 12 Pro. I've organized it based on the Pro series. The reason for the color coding is to show that these two are 7nm. The M5, M5P, and M4P below are technically 4nm, but are derived from 5nm. You can see it here as well. From the M5, the M5P emerged, and subsequently, the M5 and M4P nodes were utilized, which were newly introduced to be applied in the iPhone 14 Pro. However, when it comes to these derivative nodes, the improvements in performance and power efficiency are not very substantial. Therefore, the most significant changes are observed when moving from N7 to N5, and subsequently to N3. This transition is closely related to iPhone shipment volumes, which in turn directly impacts revenue. For example, do you see the significant jump with the iPhone 12? What happened with the iPhone 12? They applied the N5 node for the first time. Actually, the performance gain from N7 to N7P is 7% at the same power, but you can see the improvement from N7 to N5 is much higher. Similarly, when transitioning from N5 to N3, we can observe significant improvements as well. Beyond just optimizing the current process, it looks like they are aiming for a higher density design, which could mean significant changes to the entire line equipment and other related aspects. So when the iPhone 12 Pro first incorporated the N5 process, it reached its peak. Of course, this wasn't the sole factor behind its success. Nevertheless, this impressive sales performance can be partly attributed to this factor. Likewise, the iPhone 15 series has achieved record-breaking numbers, significantly outperforming its predecessors. The iPhone 14 and 16 didn't reach these sales figures. So what was the game changer for the 15? It was the adoption of the N3B node. At this juncture, with the anticipation of substantial performance enhancements, we have observed exceptionally high sales. Of course, we should take this intuitively, and we cannot say for certain that this is the sole reason. So looking at these factors, TSMC is currently leading with its 3nm and 5nm processes. This data is based on last year's third quarter, but this proportion will keep growing. The gross margin is also increasing a lot, right? However, the demand for the 2nm process is expected to be much higher. People are eagerly waiting for this technology. We mean industry leaders like Jensen Huang, Lisa Su and Apple have seen yearly sales growth. The 3nm process was too expensive to continue. Each wafer cost about $20,000. However, the 2nm process is said to cost nearly $30,000 per wafer. While there are significant power consumption issues, we can expect performance improvements, especially since our current computing capabilities are severely lacking. Computing equals competitiveness. That's why TSMC is eagerly awaiting the 2nm process. Meanwhile, analyst Ming-Chi Kuo says TSMC's 2nm process will be in iPhone 18. That's next year's second half. They anticipated this as early as last September and continue to uphold that expectation. And the yield rate, which was over 60% before, has likely increased now. In fact, the N2 node is expected to improve performance by 10 to 15% over N3. At the same performance level, power consumption will drop by 25 to 30%. This makes it appealing for those seeking better performance. Naturally, those aiming to lower power consumption would be eager to adopt this node, even if it means investing a bit more money. In fact, TSMC's Baoshan, which we commonly refer to as near Baoshan. When you visit this location, you'll notice it's packed with numerous TSMC fabs. Right here, if you look at TSMC, do you see all these fabs? There are numerous fabs here, and there's been continuous discussion about setting up the 2nm facilities. But I heard that Typhoon Kamori had a significant impact. Around 500,000 households experienced power outages, and there were some fatalities. However, TSMC's official stance is that there are no major issues. I also mentioned the Kaohsiung area. Near Tainan, TSMC is building fabs dedicated to the latest nodes and packaging technologies, with a focus on keeping these advancements within Taiwan. Meanwhile, Trump continues to exert pressure in this ongoing scenario. Nevertheless, the latest update indicates that the two facilities in this area are now fully outfitted and capable of producing a substantial number of wafers each month, signifying their readiness for large-scale manufacturing. This article talks about a target of 80,000 units for the year. Each fab can produce around 30 to 35,000 units. With a yield rate over 60%, this level of wafer production is achievable. By 2027, production is anticipated to surpass 100,000 units. However, yield rates are inherently variable. This summary from Friday Orange explains that even if the same process is used, yield rates can drop as chip sizes increase, making it difficult to set a standard for yield. Previously, I explained why Becker-Singer was so frustrated with TSMC's initial GAA process. Intel's production of large, high-performance server chips can result in a seemingly lower yield rate. Keep this in mind when considering the numbers. However, shipping over 50,000 wafers monthly suggests these wafers contain smaller chips than the current M1, like the A19 or A18. If we assume around 500 chips per wafer, producing 50,000 wafers would result in about 25 million iPhones. With an improved yield rate, this number could rise significantly, potentially surpassing 30 million units per month, demonstrating their readiness. In reality, both Intel and Samsung Foundry have already implemented cutting-edge processes such as gate-all-around and ribbon FET. Rather than implementing entirely new architectures or transistor structures, TSMC has opted to refine and optimize their existing processes. This approach minimizes significant changes and maintains their established strengths and proven recipes, allowing them to effectively leverage their existing advantages. By meticulously etching and shaping the structures, TSMC has been able to significantly reduce leakage currents, which is a testament to their dominant competitive advantage. So, I wanted to quickly summarize this for you today. Make sure to follow Reverse Engineering on Instagram to stay updated with the latest and most exciting news. Check out our international channel Unreal Tech for more updates.